right now, at this very moment. As you're listening to these words, there's something moving through space that we've been watching with intense fascination. And I want you to understand what makes this particular moment in our universe so profoundly extraordinary. Most of the time, when we talk about space, we're talking about things that are impossibly far away. Andromeda Galaxy, 2.5 million light-years. The edge of the observable universe, 46 billion light-years in every direction. These are distances that break your brain. They're incomprehensible, and that's exactly why we talk about them. But sometimes, and this is important, sometimes something comes close enough that we can actually watch it happen. We can track it in real time. We can gather data night after night after night and see the actual changes happening in front of us. That's what's occurring right now with an object that's captured the attention of astronomers, comet enthusiasts, and space agencies around the entire world. An object with the absolutely clinical name of 3I/Atlas. And here's the thing that makes your heart skip a beat. We're calling it something else. We're calling it an interstellar visitor. A comet that didn't originate from our solar system. Now, let me set the stage for you. Our solar system is surrounded by something we call the Oort cloud. It's this vast, spherical shell of icy bodies, billions upon billions of them, orbiting at the very edge of the sun's gravitational influence. Think of it like the outer suburbs of our cosmic neighborhood. It extends roughly 20,000 to 200,000 times the distance from the Earth to the sun. That's about 1 to 5 light-years away. So if our solar system was the size of a city, the Oort cloud would be a sphere that extends thousands of kilometers into the surrounding countryside. But here's the reality. Objects in the Oort cloud aren't the only things out there. The galaxy is full of comets, and some of them don't belong to us. They're vagabonds, cosmic wanderers. They travel through interstellar space, frozen and dark, until they get caught in the gravitational pull of a star system. And when that happens, when one of these ancient objects from beyond our solar system enters our neighborhood, we get to ask the most profound questions. Where did it come from? How long has it been traveling through the dark? What star system ejected it into the void? And perhaps most intriguingly, what can it tell us about how planets and solar systems form throughout the galaxy? We've actually seen this before. Oumuamua, remember that one? Back in 2017, we detected the first confirmed interstellar object passing through our solar system. Everyone lost their minds, and rightfully so. Here was an object that came from somewhere else, moving through our cosmic neighborhood. It was roughly 300 meters long, shaped like a cigar or a needle, depending on whose description you prefer. And it moved so fast that we realized immediately it had no intention of sticking around. We got a few precious weeks to observe it. And in those weeks, we learned that interstellar visitors were real. They were out there, and they were passing through. But 3I/Atlas is different. This isn't just a brief celestial hello. This is something that's behaving in ways we're still trying to understand. This is something that's changing. Let me tell you what we know so far. 3I/Atlas was first detected by the Asteroid Terrestrial Impact Last Alert System, which is what ATLAS stands for. A system designed to find near-Earth objects, asteroids, comets, anything that might pose a threat. But when the data came back, astronomers realized this wasn't a near-Earth object at all. This was something with an orbital path that didn't make sense within our solar system. The calculations revealed it came from elsewhere, from the depths of interstellar space. And it's coming close to us. Not dangerously close, but close enough that we can watch it with increasing detail as it passes behind the moon and through our inner solar system. Here's where it gets really interesting. When a comet gets close to the sun, something happens. The sun's heat begins to vaporize the ices at the comet's surface. Water ice, methane ice, carbon dioxide ice, dust trapped within. And as it vaporizes, it creates an atmosphere around the comet. We call it a coma, and often a brilliant tail pointing away from the sun, pushed by solar wind and radiation pressure. But comets don't all behave the same way. Some erupt suddenly, some brighten gradually, some fade to nothing, and some do something else entirely. They surprise us. The phrase "something just switched on" that we're hearing in the data, That's not metaphorical. That's observational reality. Astronomers monitoring 3I/Atlas have noticed something unexpected. The comet has undergone what we call an outburst, a sudden increase in brightness, a sudden increase in activity, a sudden release of gas and material from its surface. Now, why does this matter? Why are we getting excited about a comet that's getting brighter? Because it tells us something profound about the composition and structure of this ancient object. It tells us that it's still volatile, still reactive, still alive in the only sense a comet can be. It tells us that this rock, this dirty snowball, this frozen remnant from another star system, has been tumbling through the cold darkness of space for billions of years, and now that it's beginning to feel the warmth of our sun, it's waking up. Think about what we're actually witnessing here. There's a chunk of ancient material traveling through the cosmos. It was probably ejected from another star system, maybe 5 billion years ago, maybe 10 billion years ago. We don't know. It's been drifting through interstellar space, in temperatures approaching absolute zero, in perfect darkness, in profound isolation, completely alone. And then, by the cosmic lottery, by the mathematically improbable chance that its trajectory would intersect with our solar system, it enters our neighborhood. The sun's gravity catches it, slows it down, pulls it into a trajectory that brings it closer. And now, as it approaches, the radiation pressure, the solar wind, and the heat of our star begin to agitate its surface. Molecules that have been locked in ice for billions of years begin to vibrate. Ice begins to sublimate directly into gas. Coma forms. The comet brightens. And we, living on a small blue planet, get to observe the awakening of an object from beyond our world. Staggering. Genuinely staggering. But let's talk about what makes 3I/Atlas specifically interesting from a scientific perspective. First, there's the question of its origin. We can look at its orbital characteristics and make some inferences about where it came from. We can analyze its brightness curve, how it brightens and fades over time, and get clues about the composition of its nucleus. We can measure the spectral signature of the gases it's releasing and determine what elements are present. And from all of this data, we're trying to piece together, what kind of star system did you come from? Were you born around a star similar to our sun? Or were you ejected from a chaotic system with multiple stars? Second, there's the question of its activity pattern. The outburst that's being observed isn't random. Comets are scientific instruments, whether they know it or not. They tell us about solar system formation. They tell us about the primordial material that existed billions of years ago. And an outburst tells us that we're looking at a fresh surface. A surface that's being exposed to the sun for the first time in eons. When a comet goes through an outburst, it's because something has changed in its structure. Maybe a jet of material was suddenly released. Maybe a small impact disturbed the surface, exposing fresh ice underneath. Maybe structural stress in the nucleus caused a fracture. Whatever the reason, it's a moment of change. And change is what allows us to learn. Third, and this is where it gets genuinely profound, there's the philosophical question of what this object represents. We're looking at a messenger from another star. It's carrying information about how solar systems form in other regions of the galaxy. It's a time capsule from a different era of planet formation, from a different part of the Milky Way, from a star system we'll never visit. In a very real sense, this comet is teaching us about ourselves, because our solar system was formed the same way. Billions of years ago, around our young sun, the same processes were occurring. Collisions, gravitational interactions, objects being ejected into space. The material that went into making the Earth, making you, making me, all of that came from this process. And now we're getting to observe a visitor that's been shaped by the same cosmic forces. So let's talk about what happens next. The comet is passing behind the moon. This is an important moment because the moon blocks our view. But it's not without value. When an object passes behind another body, we can learn about what light is passing through its coma, the gaseous atmosphere surrounding the nucleus. We can measure how the light is refracted. We can determine the density of the gas. We can get a precise measurement of the comet's distance from us. And then, As it emerges from behind the moon and continues its journey through the inner solar system, we'll have new data. The comet will get closer to the sun. The heating will intensify. The activity will probably increase. We might see more outbursts. The tail might become more spectacular. And telescopes around the world will be pointed at it, observing, measuring, analyzing. There are infrared telescopes watching it. There are spectroscopic instruments breaking down its light into component wavelengths. There are imaging telescopes capturing photographs of the coma. There are radio telescopes detecting the material being ejected. Humanity has basically pointed every scientific instrument we have at this visitor and asked it the same question. Tell us your secrets. And it's answering. Let me paint you a picture of what happens during this encounter. Right now, 3I/Atlas is still relatively far away, millions of kilometers, but it's approaching. The sun's gravity is pulling it along its trajectory. Every day it gets slightly closer. Every day it gets slightly warmer. Every day the radiation pressure increases. The comet's nucleus is probably somewhere between 100 meters and a few kilometers in diameter. We're not entirely sure yet. It's not nearly as large as some famous comets we know. It's not as large as Comet Hale-Bopp was. But size doesn't determine spectacle. A small, volatile comet can put on a bigger show than a large, inert one. As the comet continues to approach, the heating will increase exponentially. The water ice won't just sublimate, it'll boil. Dust that's been trapped in the ice for billions of years will be ejected into space. This dust scatters light beautifully, which is why comets become so bright and visible to the naked eye. The solar wind, this constant stream of charged particles flowing out from the sun, will interact with the ionized gas, creating what we call the ion tail, typically pointing directly away from the sun. The dust tail, on the other hand, is pushed by solar radiation pressure, and it curves slightly. So if you're observing a comet, you see this beautiful billowing structure, the dust tail sweeping behind it, the ion tail pointing away from the sun, and at the center, the coma, glowing as fresh material sublimates off the surface. But here's what makes this particular encounter so compelling. We don't know exactly how active this comet will become. Some comets are docile. Some are violent. Some go through dramatic outbursts. Some go dormant. The behavior of 3I/Atlas over the coming weeks and months will tell us something crucial about its composition and structure. If it undergoes multiple outbursts, it suggests that its nucleus has weak points, structural fractures, areas where the stress from heating and cooling, from the gravitational stress of being close to the sun, is causing material to fracture and be ejected. This is actually valuable information because it tells us about the strength and porosity of cometary material, information that's not easily obtained any other way. If it undergoes a single dramatic outburst and then settles down, it might mean that the outburst exposed a fresh layer of material underneath, and that new material is now evaporating at a steady rate. Different story, different implications. If it remains relatively quiet, it could mean that the interstellar comet is substantially different from the comets native to our solar system. It might have a different composition. It might be more densely packed. It might have been shaped differently by its billions of years of solitary travel through the void. Every possibility teaches us something. And here's something else to consider. When you pass a comet close to the sun, when you subject it to the intense heat and radiation of our star, you're essentially performing an experiment that happens naturally in the galaxy. You're seeing how material from one star system responds to radiation from another star. You're seeing whether the volatile compounds preserved in this ancient object can survive the transition. You're watching the cosmos conduct its own laboratory. Scientists throughout history have done this. They've observed comets. They've tried to understand them. For centuries, comets were thought to be atmospheric phenomena, events happening in Earth's sky rather than objects in space. Then came Newton and the understanding of orbital mechanics, and the realization that comets were celestial bodies following gravitational laws. Then came spectroscopy, and we could determine what elements they contained. Then came space probes, and we could see them up close. And now, we have the remarkable situation where we can observe an object not even from our solar system. A true alien visitor. A genuine representative from elsewhere in the galaxy. Think about the sheer improbability of this. The galaxy is vast.
incomprehensibly vast.
And yet, here we are in the early decades of the 21st century, with the technology and the knowledge to detect, track, and analyze an interstellar comet. We live in a time when this is possible. And not only possible, expected. Oumuamua was the first, but it won't be the last. Our instruments are getting better. Our detection systems are improving. Within the next few decades, we expect to observe dozens of interstellar objects. Comets, asteroids, maybe even something we haven't anticipated. And each one will be a messenger. Each one will be carrying information from beyond our solar system. This is a window into the galaxy. This is an opportunity to ask questions about how the universe works on scales and timescales that dwarf human comprehension. Let's ground this for a moment in something tangible. The outburst that's been observed in 3I/Atlas, the something just switched on, is typically detected through changes in brightness. We measure something called magnitude, which is a logarithmic scale of brightness. A change of just one magnitude means the object is now 2.5 times brighter. If we've observed a change of several magnitudes, we're talking about an object that's dramatically brighter than it was days or weeks ago. This brightening could be a sudden release of dust, could be a sudden increase in gas production. It could be the exposing of a particularly volatile patch of the comet's surface. Or it could be what we call spin precession, the comet's rotation changing slightly due to the torque exerted by the asymmetric release of material. Comets are essentially top-spinning through space. Most of them rotate, and when you have asymmetric outgassing, material being ejected from one side more than the other, it creates a torque. It changes the rotation, and that can lead to all sorts of interesting behaviors. From a practical standpoint, if you're trying to operate a spacecraft near a comet, this is exactly what you worry about. You need to predict the comet's behavior, because unexpected outbursts mean unexpected forces. And unexpected forces can throw off your trajectory. But we're not putting spacecraft near this one. Not yet, anyway. What we're doing is far more elegant. We're observing from afar. We're gathering data. We're letting the comet reveal itself to us through its behavior and its light. Here's another layer to the story. The question of where 3I/Atlas comes from is genuinely difficult to answer. We can look at its orbit, the elliptical path it's following, and we can extrapolate backward. We can see where it came from, roughly. We can see which direction it was traveling. But pinpointing the exact star system that ejected it? That's much harder. The galaxy is old, nearly 14 billion years old. Our sun is about 4.5 billion years old. And this comet? It's been drifting through space for some substantial fraction of the galaxy's lifetime. It could have come from any of billions of star systems. It could have been ejected from a system with multiple massive stars, where gravitational interactions are common. It could have been ejected from a system like ours, where interactions are rarer but still possible. And here's the beautiful part. We may never know for certain. We may never trace this object back to its origins. But we don't need to. The object itself is the answer. By studying its composition, its structure, its behavior, we're learning about the processes that happen throughout the galaxy. There's a concept in astronomy called exoplanet atmosphere characterization. When a planet passes in front of a star, we can analyze the light that passes through its atmosphere. We can determine what gases are present. We can understand the composition of worlds we'll never visit. And in a way, a comet is doing something similar. It's letting us analyze material from a star system we'll never visit. It's giving us a sample of the raw material of the solar system that created it. This is why this encounter is scientifically valuable. And it's why, despite the fact that you probably haven't heard much about 3I/Atlas in the mainstream media, astronomers around the world have been absolutely glued to their instruments. Let's talk about the moon's role in this story. The moon is in the way right now. The comet is passing behind it. From our perspective on Earth, this is actually a significant moment. We can observe the comet as it disappears behind the lunar disk. We can watch for it as it emerges on the other side. And in those moments of disappearance and reappearance, we can gather precise information about the comet's distance, its velocity, and the structure of its coma. This is called an occultation. When one celestial body passes in front of another, blocking it from view. It's a classic astronomical technique for measuring distances and getting precise positional information. It's been used for centuries. When the moon passes in front of a star, observers on Earth can note the exact time of disappearance and reappearance, and they can triangulate the position with remarkable precision. For a comet, it's slightly different because comets are extended objects. They have a coma around them, so the disappearance isn't instantaneous. We can watch as the coma gets increasingly distorted by the lunar gravity. We can watch as the brightness gradually decreases as more and more of the coma gets blocked. And we can gather information about the density and structure of the coma from how the light is refracted and scattered. The moon is not a passive observer in this story. It's an active participant in helping us understand this visitor from beyond. And here's something poetic about it. The moon is an ancient object itself. It formed nearly as long ago as the Earth. It's been orbiting us for over 4 billion years. And now, by its position between us and 3I/Atlas, it's helping us understand an object that's been drifting through space for an even more ancient epoch. There's a conversation happening in space right now, and we get to listen. An ancient Earth-born object and an ancient galactic object coming into alignment, helping us understand the universe better. Now, let's consider what comes after the lunar passage. Once 3I/Atlas emerges from behind the moon, it will continue its journey toward the sun. The heating will intensify. The activity will likely increase. We might see the coma expand. We might see brighter outbursts. We might see structural changes as the comet responds to the increasing thermal stress. This is where the real drama happens. This is where we see the comet at its most magnificent. Comets are brightest when they're closest to the sun. This is where the heating is most intense, where the outgassing is most vigorous, where the tail is most spectacular. Famous comets in history, Comet Hale-Bopp, Comet Hyakutake, Comet Ikiyasaki, achieved their greatest brightness near perihelion, which is the point of closest approach to the sun. For 3I/Atlas, we're still approaching perihelion. Hasn't gotten there yet, so the best is yet to come. Whether this comet will be naked eye visible depends on several factors. It depends on how active it becomes. It depends on how much dust is ejected. It depends on whether those outbursts continue or increase. And it depends on the geometry, on whether the tail points toward us or away from us, on whether we have a good view of the illuminated side of the coma. But even if it doesn't become bright enough for naked eye observation, it's still scientifically spectacular. Telescopes will capture it in extraordinary detail. We'll see the structure of the coma. We'll see the tail. We'll see the jets of material being ejected from the nucleus. And through it all, we'll be gathering data about this visitor from elsewhere. There's something to consider about the nature of knowledge and discovery here. For most of human history, comets were mysterious phenomena. They appeared suddenly, trailing through the sky, inspiring awe and fear. They were signs and portents. They were omens. People tried to understand them, but understanding was limited by what was visible to the naked eye. Then came telescopes, and suddenly comets became scientific objects. We could measure their positions precisely. We could track them night after night. We could determine that they followed orbital paths, governed by the same gravitational laws that govern planets and stars. Then came spectroscopy, and suddenly we could determine what comets were made of. We could see the fingerprints of different elements in the light they emitted. We could say with certainty that comets contained water, methane, carbon dioxide, complex organic compounds. Then came space probes. Missions like Giotto, which flew past Halley's Comet in 1986 and sent back the first close-up images of a cometary nucleus. We could see the actual surface. We could see that it was dark and irregular and porous, pitted with jets where material was being ejected. And now we have a comet from beyond our solar system, a comet that's traveled through the depths of interstellar space. And we can observe it in real time, gathering data across multiple wavelengths, from radio to infrared to ultraviolet, painting a complete picture of this ancient object. This is the arc of scientific progress. Each generation adds new capabilities. Each generation asks new questions. Each generation, the universe becomes more knowable. Let me talk about what happens to the comet after this encounter. Comets are fragile objects. Many comets are destroyed by their encounter with the sun. The tidal stresses are enormous. The heating is extreme. And sometimes, a comet simply doesn't survive. It fragments. It breaks apart. Sometimes a single large piece becomes several smaller pieces, and all of them continue on their original orbits. Sometimes the nucleus shatters into a cloud of smaller bodies. But 3I/Atlas, being an interstellar visitor, is actually in a different category than most solar system comets. It came from outside our solar system, which means its orbit is different. It probably came in on a hyperbolic trajectory. It's not bound to the sun forever. It's just passing through. This means that after this encounter with the sun, after it reaches perihelion, it will start to recede. The sun's gravity will slow it down, but it won't be enough to capture it permanently. Eventually, it will escape the solar system entirely. It will head back out into the depths of interstellar space. And after it leaves the vicinity of the sun, its surface will start to cool again. The outgassing will cease. The coma will dissipate, and it will become dark again, cold again, dormant again, and it will drift through space, carrying with it the memory of its encounter with our star, carrying with it the heat and the radiation that changed its surface, carrying with it the dust that was ejected into space and may, someday, collide with some other planet or comet or star. Eventually, in billions of years, it will be caught by another star, another encounter, another heating, another opportunity for scientists, if they exist, on some world in the future to study this ancient wanderer. This is the life cycle of an interstellar comet. It's solitary, it's long, and it's a story that spans the ages of galaxies. Now, let's talk about what this means for us. The discovery and observation of 3I/Atlas is significant in ways that go beyond just the scientific data we're gathering. It's significant for what it tells us about the nature of our place in the universe. For a long time, humanity believed that we were unique, that our solar system was unique, that the sun was special and everything revolved around it. This was partly correct. The sun does cause everything in the solar system to orbit, but it was also deeply narcissistic. We thought we were the center of creation. Copernicus showed that wasn't true. We're not the center of the solar system. The sun is, and the sun is just one star among billions. And those billions of stars each have their own systems, their own worlds, their own stories. And now we're observing objects that are visiting us from those other systems. We're seeing them with our own instruments. We're analyzing them. We're asking them questions. This is more than science. This is philosophy. This is an acknowledgement that we're part of a larger cosmos, that we're citizens of a galaxy with billions of stars, that the material that makes up the comet is the same material that makes up our world, the same material that makes up our bodies. Think about that. The carbon in your cells, the oxygen you breathe, the calcium in your bones. All of that came from stellar nucleosynthesis. It came from stars that died billions of years ago. It was ejected into space. It was incorporated into our solar system. It was incorporated into the Earth. And now it's part of you. And this comet 3I/Atlas? The same is true. It's made of the same elements. It formed in the same way. It came from a star system that might be billions of light years away, but it's fundamentally connected to us through the physics that governs the universe. In observing this comet, we're observing ourselves. We're seeing our own cosmic origin story. We're glimpsing the processes that created us. This is why the something just switched on is so profound, because it's not just a change in brightness. It's not just an outburst of gas and dust. It's a moment of awakening. It's a moment when an ancient object from the depths of space is responding to stimulation. It's a moment when we, as observers, are privileged to witness something that rarely happens on a timescale accessible to human lifespans. Most cosmic processes happen too slowly for us to see in a lifetime. Stars form over millions of years. Galaxies collide over billions of years. But a comet outburst? That happens on a timescale of days or weeks. We can actually watch it happen. We can gather data before and after. We can measure the change in real time. And that real-time observation is the key to understanding. Because in those moments of change, the universe reveals its true nature. In those moments, we see the mechanisms that drive cosmic phenomena. We see the physics in action. So what should you take away from all of this? First, we live in a universe where objects travel between stars, where material from one star system can visit another, where the boundaries between stellar neighborhoods are permeable. This sounds like science fiction, but it's observational reality. Second, we have the technology and the knowledge to detect and analyze these objects. We're not passive observers anymore. We're active participants in understanding the cosmos. We can point our instruments at the sky and ask specific questions and get answers. Third, the universe is far more connected and far more dynamic than we might think. This comet is a messenger. It's carrying information from its home star system. It's telling us about the diversity of planetary systems, about the kinds of processes that happen throughout the galaxy, about our place in the cosmic context. And fourth, this is just the beginning. We're in the early days of interstellar object science. More will come. Our detection systems will improve. We'll have more opportunities to study these visitors, and each one will add to our understanding. 3I/Atlas is passing behind the moon. Something has switched on. An ancient object from the depths of space is briefly entering our neighborhood, briefly bathed in the light of our sun, briefly revealing secrets that have been locked inside it for billions of years. This moment won't last. The comet will pass. The outburst will fade. The object will continue its journey and eventually escape our solar system. It will return to the cold darkness from which it came, and we will be left with data, with measurements, with images, with the raw material of discovery. And that's enough, because discovery is never about the moment of observation. It's about what the observation tells us. It's about the questions it raises. It's about the understanding that grows from that investigation. We are living in a moment where the universe is handing us a gift, an object from beyond our solar system traveling through space and briefly, just briefly, passing close enough that we can study it. We can learn from it. We can use it to understand our place in the cosmos. That's not something to take for granted. That's something to be genuinely, profoundly grateful for, because the universe doesn't hand out opportunities like this very often, and we should be ready to take advantage of them. So keep watching the skies, keep monitoring the data, keep looking up, because 3I/Atlas is out there, and something has switched on. And for those of us who understand what that means, it's one of the most remarkable moments in human history.